All right, here we go. I'm Frank Bohlen, for those of you that don't know me. I'm a physical oceanographer at the University of Connecticut Department of Marine Sciences and a sailor. I, over the years, have had the opportunity, I guess as you age has got to be good for something, right? You can look back on 70 years of development of weather. Many of the races that I participated in, I've been the navigator. So we've had an opportunity to look at the variety of formats, at the variety of data quality, and we come to today, the land of apps. To tell you the truth, it's come to a state of sort of sensory overload. So one of the things we hope to come out with today is a sense of where we are, where we might be going, and some of the key tools to use. And the key tools to use may differ. I might use one set and you might use another, but you're not going to be using all the tools available. It's just plain too much information. Also, we hope to give you a sense of the nature of the enemy, your dance partner, why our understanding might be less than perfect. That little yellow box on the program is something that I want you to take a look at now as we get into this. You'll see it again in a moment. And at the end of the day, you want to ask yourself if you know some more things about some of the items, the bullets in that box. So let's begin with a little bit of history. It's always well to look back, if for no other reason than to avoid the mistakes of the past. What are we dealing with? Marine weather and sea state. It says it right up there. State of the art, state of the science. Make no mistake, there's a fair amount of art involved in this. And that may be part of the problem. Some of us are better artists than others. Okay? Weather is a fascinating subject. It controls, to some extent, our life every day. What you wear and what you do, whether you go into the house or out of the house, and has for thousands of years. You can look back into history, probably around 3,000 years back, and see that there were some attempts to understand, but an awful lot of it was legend. God's wilderness, the conditions intended to punish sin. That may bring it closer to home for some than others. And we dated, if we can define sin today, you start looking at about 300 BC, from 600 to 300 BC, you start seeing some attempt to make use of it in calendars and the like. And it's remarkable to realize that around 300 years before Christ, our friend Aristotle here wrote a treatise on meteorology that, when you read through it, has some remarkable insights given the period. 300 years before Christ, Aristotle's talking about vertical structure in the atmosphere. Of course, meteorology deals with things that come from the air. Some say fall from the air, but from the air. Aristotle's work was lost to history for about 1,300 years, 1,400 years. And we were living with, all through that period, legend. You know, all sorts of folklore around the sea, right? Gray socks leaving port on Friday and the like. There was similar legend associated with the weather. The black-handled knife. The black handle because that was a handy way to handle water spouts. We could cut down water spout with a black-handled knife, right? You can read in Horace Beck's great book on folklore in the sea. The science of meteorology, science in general, really didn't get going until after the scientific revolution, around late 1500s, early 1600s. And these are three principal figures that you all know: Galileo, the ultimate empiricist; Francis Bacon, the father of the scientific method; and hypothesis. You test the hypothesis, you gather some data to test the hypothesis, and you go back out and revise the hypothesis. And then, of course, Sir Isaac Newton, who together with Leibniz gave us the calculus. So you not only had some folks interested in experiments, but some folks interested in the why of the experiment, and here we could quantify some of the results. Not till around 1500 or so, 1600. Through the 1800s was a major period of exploration and theory development. And the important part of science, as it says here, is systematic acquisition of information within a theoretical framework. Systematic acquisition of information. Well, you needed some sort of standards to use. And Luke Howard, an amateur meteorologist, chemist and amateur meteorologist, gave us the first classification of clouds that we use to this day, early 1800s. Okay? For instance, here our old friend Beaufort. You all know Mr. Admiral Beaufort well. If you don't, here's the Beaufort Scale. He also encouraged his captains to keep regular logs. It was the beginning of systematic log keeping. And in this country, Matthew Fontaine Maury did the same thing. I put in Espy here. There was a whole series of scientists and explorers. You started seeing balloon elevations, expeditions in the 1800s looking at vertical structure. But I put in Espy because he's sort of my hero, the role of the latent caloric. We're going to hear a little bit today about latent caloric. You all know about latent caloric, right? Latent heat transport associated with the evaporation and condensation of water vapor over the vertical. Okay? And Espy was one, is working at the Franklin Institute, and was responsible for one of the first US weather maps. 1840, the first US weather map. And it was basically a compilation of information from observing stations, most of them around the Northeast. Looks like the National Weather Service grid in the early days, eh? Just a close-up of that. You can see barometric pressure, wind speed, direction, air temperature, pretty fundamental kind of stuff all at the surface. Another hero of mine, Robert Fitzroy. Everybody knows Fitzroy. Fitzroy was Darwin's captain. Okay? So he was the skipper of the Beagle before Darwin, during Darwin, after. When he came back, you could spend an hour talking about Fitzroy, but he was credited as the first who spoke of forecasting. When he did, of course, in the mid to late 1800s, he was ridiculed. What kind of forecast what's going to happen tomorrow? We can hardly know what's going on today, sort of a thing. He ended committing suicide, and some said he did it because of the weather, but there were other factors that were involved. But he came up with the first forecast, which looks something like this, from a series of observing stations. He was encouraging the Admiralty and the British Board of Trade to set up stations around England, and the French were picking up the same thing on mainland Europe, and you started to see some things like probable weather tomorrow, sort of a thing. Again, fairly fundamental. We jump now to 1900, and the Norwegian School. Physical oceanographers put a lot of stock in the Norwegian School. They not only set in place the fundamentals for working on atmospheric circulation, they set in place the fundamentals for working on ocean circulation. And Bjerknes' family were major players in that. He set out a fundamental equation of motion. And believe it or not, everything you're talking about today is built today, everything that we will be talking about today is built around the same set of equations. Very fundamental kind of stuff. And they're up here and we could go through them. But the idea was that he could predict the dynamical and physical condition of the atmosphere at a later time if the initial conditions, boundary conditions, could be specified. And that's a big if. And that, to some extent, as you see, we play through today, plagues us still. We don't have an infinite number of observing stations, and we're always worrying about the specification of initial conditions, particularly when we're dealing with models. Speaking of models, here is Richardson, and he came up with a solution. He's credited with being the first to solve the Bjerknes equations, some form of them, numerically. And he did it fundamentally by hand. He got a 6-hour forecast. It took 26 days to do it. Some might wonder if we aren't doing some of that today, but that's another story, okay? Really, so there you were, 1925. We're now to the computer. When we got involved in oceanography, we were still doing a lot of calculation with Frieden calculators, the mechanical calculator, no HP 35s or TI instruments, okay? That's 1960. Here's 1950. ENIAC came along, and it too went after the numerical solution. And in this case, they were able to get a 24-hour forecast in about 24 hours. So, of course, the computing power from ENIAC was about equivalent to what you have in your pockets today. 1957, 1960, we're getting close, huh? Some of us can even remember 57 and the launch of Sputnik. Okay, satellites. Teros was our first satellite, lasted 78 days, but it really provided some valuable information back to us. Not the least of which was some views of the whole of the Earth. This, of course, is the famous blue marble from NASA, but it gives you an idea, you're going to see this again, of the coupling between the atmosphere and the ocean. The challenge that atmospheric flows, the problem is that atmospheric flows, and in fact most geophysical flows, are turbulent. If you don't know what that means in terms of flows, you should go look it up. This is the problem that we have. The flow is turbulent. There are two classes of flow. The fluid dynamicist talks about laminar, where the streamlines in the flow are straight and parallel. And you can pretty well specify deterministically what the shear stress, what the friction, what the velocities are in that laminar flow. When the flow goes turbulent, when you stare at that shower in the morning or you stare at the water coming out of the spigot into the sink and you see all that irregular looking flow, that flow is turbulent. The streamlines are not straight and parallel. They tend to be quite a few rounding back and forth, eddies. The flow is classed as a whole fleet of eddies. That's why Richardson was talking about the vorticity, the swirls, and the different scales of the swirls. When the flow is turbulent, you can no longer specify its characteristic deterministically. 2 and 2 is in 4, deterministic. 2 plus x may be 4. If x is a 2, then but if it's something else, it's something else. We can't describe it deterministically, we'd best describe it stochastically. The weather forecasts that we receive do not say, believe it or not, do not say it's going to rain this afternoon. But they do. I just read it. No. The real truth is, it may rain this afternoon. Now, there are occasions, if I was to smack Ralph, it's a pretty high probability that he might smack me back. But from a stochastic standpoint, you say, I'm going to smack Ralph, and he may smack me back. He's going to run out the door instead of smacking me back, or some such. You with me? Understand that. That is going to permeate what we talk about today. The fact that the flows, the fact that the state of the atmosphere we're interested in is stochastic because the fundamental flows are turbulent. Ed Lawrence at MIT was the one that coined the butterfly effect. He was trying to work on some dynamics of tornadoes, and he was running some models, and he took a break, and he came back, and it was getting late in the day, and he took his initial conditions for the model, and he truncated the last 3 places in the numbers, went to whole numbers. And when he ran the model, he got completely different results than what he had been getting earlier in the day. And he realized just how sensitive the models were to the initial conditions. And he said it's like trying to figure out what causes a tornado. It could be something miles away, a butterfly going by, shedding some eddies. John Isaac's out at Scripps trying to forecast what goes on with tornadoes, the frequency of tornadoes, related to the frequency of shipping in Ohio and North Texas, okay? On the weekends, there aren't as many trucks going up and down the road, shedding the eddies from those big things they have up on top of the vans, eh? And everybody sort of poo-pooed the whole thing. But that's the concept, that the systems that we deal with, very sensitive to the internal conditions. And remember what we said about sampling. You're not sampling every spot, so you can't specify absolutely the initial conditions everywhere. Carry that with you. Whoop. That's interesting. We went back. It's here. That's one reason why today we're getting to see more and more probabilistic forecast information or probabilistic guidance. This is a page from a National Weather Service site. It talks about the probability, this comes from the GFS model, probabilistic wind speed guidance, okay? And this is for a 20-knot wind, and it looks like the reds are 95% probability that you're going to see a 20-knot wind in this area. The US is over in this area. And it runs out to 16 days. Now, one of the tricks, of course, is what you do with this. If you see it, you're figuring to go for a sail. But we're starting to see the recognition of the stochastic nature of the forecast, and they're trying to provide you with some information on just how probabilistic is this whole thing. We'll see more of this. This is a time series of an anomaly between the forecast and the observed 500 millibar surface. And it says here that we're getting better and better with time. We run from 1980 to 2010, and it looks like we started out at something like 5 to 6 days forecast accuracy, and we're out to something like 8 to 10 days. But realize that correlation is only 60%. 50-50. Yeah, we said the forecasters are out there flipping a coin, right? There's been an improvement, and we'll hear more, I'm sure, from Joe Sinkwitz this afternoon about what they're thinking about on that. And you just saw forecast model probabilistic stuff running out to 16 days. Don't be terribly surprised if the accuracy of all of that dies off after something like 4 to 5, 6 days. We'll be talking more about that. So, on that box, it says the nature of the problem. Here's what weather is. It's a dynamic property which displays significant spatial and temporal variability due to a whole variety of factors. Hot, cold, the roughness at the surface. Okay? The resulting flows are turbulent, meaning that they are, to some extent, chaotic. Some great books on chaos. Entertaining reading, actually. And best described by statistical methods, for example, probability, yet most forecasts are taken to be deterministic. Right? You look at it, you say it's going to be 20 knots of wind this afternoon. The fact that we're getting pretty good at that doesn't mean we're getting perfect at it. Forecasts of the future weather depend on understanding of atmospheric physics. We're still learning. From an analytical standpoint, the fundamental problem with the turbulent flows is that they're the characteristic of the internal friction in the flow. When you go to solve the equations, there are more unknowns than there are equations, if you remember back to your math days. Okay? So what do we do about those hanging chods that are out there? We lop them off. On what basis? We guess. It looks small enough that it isn't going to be a problem. Let's trim it off. But just as Ed Lawrence found out that sometimes trimming off that last set of small numbers in the thousandth place can have a significant effect, trimming off willy-nilly in an effort to close these turbulent equations can sometimes lead to problems. Okay? A combination of observational data. Most of us are sailors. You can sail many miles without seeing much in the way of observation, a buoy. You'll see it from satellites. You may not see the drifters that we're putting out there more and more, but it's not terribly surprising that sometimes the marine weather forecasts suffer because of a lack of observational data. Take a look at the observational network over land and compare it to what goes on over sea. Okay? The models, they're getting better and better. Accuracy is dependent on the adequacy of each of these components. At the end of the day, you want to carefully consider for your purpose where this all fits in. So, there's a little bit of history and a little bit of the setting that we're going to be operating in today. Thank you very much.